Imagine you are an astronaut. You're far above Earth, gazing down at our beautiful blue planet. Inside your spacecraft, you let go of a pen. Does it fall to the floor? No, it just hangs there, suspended in midair. This strange and wonderful environment is what we call microgravity. The micro part means very small, so microgravity means a condition where the pull of gravity feels very, very weak. It's not that gravity has completely disappeared, not at all. It's just that its effects are perceived in a profoundly different way when you are in orbit, constantly falling around a celestial body like our Earth. This sensation is often called weightlessness, a term that captures the feeling quite well. When we talk about microgravity, we are describing a state where objects behave as if there is very little gravity acting upon them. Think about jumping up and down on Earth. Gravity always pulls you back down. In a microgravity environment, like on the International Space Station, that downward pull seems to be almost gone. Astronauts and objects alike float effortlessly. This isn't because they have escaped Earth's gravity entirely. The ISS is still very much within Earth's gravitational influence. So why do astronauts and objects float so gracefully in space as if they are lighter than a feather? The primary reason is that they are in a constant state of free fall. Imagine you are in an elevator and suddenly the cable snaps. For a terrifying few moments before the emergency brakes kick in, you and anything you are holding would float. You would feel weightless. This is because you, the elevator, and everything inside it are all falling at the same rate due to gravity. There is no upward force from the floor pushing against your feet, so you don't feel your own weight. This is precisely what happens in orbit. Astronauts aboard the International Space Station are not floating because they are beyond Earth's gravity. In fact, at the altitude of the ISS, about 400 kilometers, or 250 miles up, Earth's gravity is still about 90% as strong as it is on the surface. That's a significant pull. The reason they float is that the space station and everything within it is continuously falling the Earth. It's moving sideways so fast, about 28,000 kilometers per hour, or 17,500 miles per hour, that as it falls towards Earth, the Earth's surface curves away beneath it at the same rate. This creates a continuous, unending fall. It's a common misconception that there is no gravity in space. This idea often comes from watching astronauts float, leading people to think they have escaped Earth's pull entirely. However, gravity is a fundamental force of the universe. It was Isaac Newton who first described it, realizing that the same force that makes an apple fall from a tree also keeps the moon in orbit around the Earth. This force extends infinitely, although it does get weaker with distance. So, even in the vast emptiness between galaxies, gravity is still at work, albeit very faintly. For spacecraft orbiting Earth like the International Space Station, gravity is very much present and accounted for. As mentioned, at the ISS's altitude, Earth's gravitational pull is still about 90% of what we feel on the surface. How does something stay in orbit, seemingly defying gravity by not crashing back to Earth? The secret lies in achieving the perfect balance between its forward motion, its horizontal velocity, and the downward pull of gravity. Imagine throwing a ball. It travels forward for a bit, but gravity pulls it down, and it eventually hits the ground. Now, imagine you could throw that ball with incredible speed. It would travel much farther before landing. If you could throw it fast enough, as it falls towards Earth, the Earth's surface would curve away beneath it at the exact same rate. This is the essence of an orbit, a continuous fall around a planet. The International Space Station, for example, is constantly falling towards Earth due to gravity. However, it's also traveling horizontally at a tremendous speed, approximately 28,000 kilometers per hour, or 17,500 miles per hour. This immense sideways velocity means that as the ISS falls, it also travels a great distance horizontally. By the time it has fallen a certain amount, the Earth has curved away underneath it by the same amount. So it keeps missing the Earth, effectively falling it. This is not a delicate balancing act against gravity, but rather a clever utilization of it. Maintaining an orbit isn't entirely effortless, though. Even at high altitudes, there's a tiny amount of atmospheric drag, a faint friction from the wisps of Earth's upper atmosphere. Section 5. Why we study the float. NASA's microgravity mission. NASA and other space agencies around the world invest significant resources into studying microgravity. But why is understanding this floating environment so important? One of the primary drivers is human space exploration. If we plan to send astronauts on long journeys, perhaps to Mars or beyond, we need to understand how the human body and various critical systems behave in the prolonged absence of significant gravitational stress. The effects of microgravity on the human body are profound and varied. Astronauts experience bone density loss, muscle atrophy, changes in cardiovascular function, and shifts in their immune system. Studying these changes helps NASA develop countermeasures to keep astronauts healthy during extended stays in space. Section 6. The Human Element, Our Bodies in a Weightless World. The human body is a remarkable machine, finely tuned by millions of years of evolution to thrive under Earth's constant gravitational pull. When that pull is significantly reduced, as in microgravity, our bodies begin to change in fascinating and sometimes concerning ways. One of the most immediate effects is a shift of fluids. On Earth, gravity pulls fluids down towards our legs and feet. In space, without this strong downward pull, fluids redistribute, moving towards the upper body and head. This can lead to a puffy face, skinny bird legs, nasal congestion, and even slight changes in vision for some astronauts. Another significant impact is on the musculoskeletal system. Our bones and muscles are constantly working against gravity on Earth. When you stand or walk, your bones support your weight, and your muscles work to keep you upright and move you around. In microgravity, this constant loading is removed. Section 7. Cosmic Laboratories, Experiments Beyond Earth. The microgravity environment of space, particularly aboard orbiting platforms like the International Space Station, serves as an unparalleled laboratory for scientific discovery. Many phenomena that are difficult or impossible to study on Earth due to the overwhelming influence of gravity can be observed in their purest forms in space. This allows scientists to delve deeper into the fundamental laws of physics, chemistry, and biology, leading to breakthroughs that can have far-reaching implications both for future space missions and for life back on our home planet. One major area of research is materials science. On Earth, when you try to mix substances with different densities like oil and water, gravity causes them to separate. In microgravity, this sedimentation effect is greatly reduced, allowing for the creation of more uniform mixtures and alloys with unique properties. Similarly, the process of crystal growth is significantly affected. Gravity can introduce defects into crystals as they form. In microgravity, larger, more perfect crystals can be grown, which are invaluable for industries ranging from pharmaceuticals to electronics. Section 8. Faking Freefall, Simulating Microgravity on Our Planet. While sending experiments and astronauts into orbit provides the best quality and longest duration of microgravity, it is also very expensive and complex. Fortunately, scientists have developed several ingenious ways to simulate microgravity conditions right here on Earth, allowing for more accessible and rapid research, testing, and training. These methods don't perfectly replicate the space environment, but they offer brief, valuable windows into the world of weightlessness, enabling a wide range of preparatory work before committing to a space mission. One of the most well-known methods is parabolic flight, often conducted in specially modified airplanes. These aircraft, sometimes nicknamed vomit comets due to the nausea they can induce, fly in a series of steep climbs and sharp dives. During the upward arc and subsequent freefall portion of the parabola, occupants inside the plane experience about 20 to 25 seconds of near weightlessness. Section 9. Conclusion: Understanding Microgravity, Unlocking Space. The study of microgravity, this intriguing state of apparent weightlessness, is far more than just a fascinating scientific curiosity. It is a cornerstone of our ability to explore the cosmos, to live and work beyond Earth, and to push the boundaries of human knowledge. From the way astronauts float effortlessly inside the International Space Station, to the subtle changes in how flames burn or crystals grow, microgravity reveals a universe where the familiar rules of earthbound physics take on new and surprising dimensions. This understanding is absolutely critical for the future of space travel and scientific advancement. Grasping how objects and, crucially, human beings behave in microgravity is essential for designing safe and effective long-duration space missions. The physiological adaptations our bodies undergo, the bone density loss, muscle atrophy, and fluid shifts, present significant challenges that NASA and other space agencies are actively working to overcome through research conducted in this unique environment. The countermeasures developed, such as specialized exercise regimes and nutritional plans, are vital for keeping our explorers healthy as they venture further from home, perhaps one day to Mars or even beyond our solar system.